Hello, Calculus and Vectors class. You guys are all looking very well today. I hope you guys are staying safe and washing your hands regularly. Hopefully you guys are feeling pretty good with 3.4 and everything to do with intersections of lines. If not, make sure you come and check in with me and we'll get it all sorted out. But luckily 3.5 does not require the knowledge from 3.4 to really understand it. And in fact, maybe if you get this one, then it will help to deepen your understanding and figure out 3.4 a bit more. What I will say is, of all of the intersection problems that we're going to deal with, I think you guys are probably going to like this one the most because of all the solutions, is probably the simplest to find. Before we deal with the solutions, though, we need to talk a little bit about the types of intersections. Now, just like before, the way that we find intersections is we assume that there is intersection at a point, and then we see what happens. So I'm going to kind of explain that as we go too. So for option one, we could have a line that intersects the plane at one singular point. And if that's the case, when we do our solution, we'll get something like x equals some number and y equals some number, like we normally do with something like elimination or substitution. Pretty much the exact same principle. Now, if we look at option two, we have a line inside the plane, in which case there's infinitely many possibilities. So when we try and find an intersection at a point, we're going to get something that is universally true, like 0 equals 0, or 1 equals 1, or 7 equals 7, or something like that. Now for option 3, we have a line that it's running parallel to a plane, which means there is no point of intersection. And when we try and find one, we're going to get something that we know never to be true, like 0 is equal to 7, which we know is absolutely never true in any circumstance. Basically, with all these problems, we're starting on the assumption that there is an intersection, and then we're going to find something that's either true in a specific circumstance, like option one, something that's always true, or something that's never true, and that's going to tell us what type of intersection that we have. So now that we talked about those, let's start dealing with some of these problems, shall we? Now, example one, we have a line in a plane, and we're asked to find the point of intersection between that line and the plane. And we're going to assume that there's one. There might not be. Sometimes it's asking to determine the point of intersection, and there might be no solution, and that happens too. But for right now, let's start trying this, and let's see what happens. Now, just like usual, we can use basic substitution principles to help us with this. And what you're going to notice is that we have, with our parametric equations, we have an x, y, and z equation. And in our plane, we have an x, y, and z. And we know that if there is a point of intersection, that those x, y, and z should be exactly the same numbers. As it turns out, all we have to do is sub in this expression for x in where x is, this expression in for y, this expression in for z. And that's what we get when we flip down to step 2. All we've done is we've subbed in those parametric equations into the equation of the plane and started to solve. Now I'm assuming that you guys are all rock stars with isolating and solving equations, so I'll leave that for you guys to figure out. If you're not sure about, come talk to me. But what I will tell you is if you do it correctly, the solution is t equals -1. So basically, thinking back to what we said before, we said we're starting on the assumption that there is an intersection. And what's going to happen by the end is we're going to find the circumstances under which there is an intersection. So the only circumstance that's required for there to be an intersection is that t is equal to -1. So what that means is if we look back at our line 1, we had that t there. If we subbed in t equals -1 and did all the arithmetic, we could actually solve for that point. You can do that. You can do that in the vector equation if you want. It still works the exact same way. But personally, I find working with the parametric equation is a little bit easier. So that's what I've done down at the bottom. So I've taken our 3 parametric equations and I've subbed in -1 into each one. And when we do that, it generates our 3 coordinates, which are 2, 5, and 10. So finish off with the therefore statement. The point of intersection is 2, 5, 10. So that's the example where you have a point of intersection, and you're going to have t equals some value, and you get your x, y, and z values from that. Let's go on to another example. It says, again, determine the point of intersection between the line and the plane, which of course also means try to determine if there is a point of intersection. So we're going to do the exact same thing. And in this one, they were very nice to us. They gave us the parametric equations already, so it saves us a step. So that first step would still apply if we were doing a vector equation, but since they've done it for us already, we don't need to do it. We're just going to take those three expressions for x, y, and z and plug them into our plane. And that's what we've done down below. And once we've solved all that, you guys can hopefully go through and do that yourself, but you should get a result of 0t equals -3. So again, at this point, we ask ourselves, for what values of t are we going to have a true statement here? What values of t can we multiply by 0 to get -3? And of course, we know that no values of t are going to work. So in this case, there's no values of t that satisfy our assumption that this line, this plane intersects. So we have to conclude that there is no solution. It's parallel and distinct. And spoiler alert, we dealt with 2 of the 3 types of solutions. We're going to deal with a third one in this case, but we're going to do it the exact same way. So let's try it, shall we? So first step, we're going to take our 3 parametric equations. We're going to sub them in to our plane, and then we're going to solve. And this one, essentially the same basic method of solving, but in this case, if you did it correctly, you should get a result of 0t equals 0. So what that means is, it's asking us what values of t satisfy this equation. What values of t can we multiply with 0 and get a result of 0? And the answer is any single value of t that's a real number is going to work for us. So t is an element of the real number set, so therefore the line is in the plane. There is infinitely many solutions. Now, before we leave this lesson, just like the last one, there is one more little topic that really links back to lines and planes, which is the distance from a point to a plane. And we say distance from a point to a plane. It could be just a single point, but we know that if the line and the plane are parallel, then any point is gonna tell us distance between that line and the plane. Okay. We know there's 3 options. Either it's going to be coincident, in which case it's going to be a distance of 0, which we already know, or it could be intersecting at a point, in which case, again, it's going to be 0. So this only applies when we have a line that's parallel to the plane. But we can still use this, whether it's a line parallel or if it's a singular point, we can use that to find it. And again, just like the last lesson, with skew lines, we're looking at the shortest distance. So we're trying to find the distance pretty much straight down, the common perpendicular that connects us to our plane. Now, I mentioned in the last lesson that I wasn't going to give an explanation because there's something in this lesson that connects back to it, and this is the part here. So I'm going to give you a little bit of an explanation as to how this works. Now, in this case, we have this formula here, d equals n dot pq, all absolute value, over the magnitude of n, which again we know is the projection of PQ onto n. And again, for this one, we're going to have our point P on our plane, or on our line, or outside, and we're going to have some point Q on our plane. It could be over here, maybe. Actually, scratch that. Say it's this one here, Q. Now, we have that vector there, and we have our normal vector, which is this one here. So it might not necessarily be this length. It could be longer, it could be shorter, which is why we use the projection. But we want it to go in that direction because we said we want the common perpendicular. We know that the distance between our point and our plane is going to run in the same direction as our normal. So the projection just gives us a convenient way to shift our PQ onto that normal vector and have it be the right distance. Again, we just cast a shadow from PQ onto N. So in fact, this formula works for this application. So now that we have talked about that, let's talk about how we use this to help find the distance between a point and a plane. So just like any other problem, we have to start by trying to figure out if what type of intersection this is. So in this case, we're going to test a point, and we're going to see if point P is in the plane. So we're going to sub it in, and we get 4 times 10 plus 2 times 3 plus negative 8 minus 16 equals 0. We get something like 22 equals 0. Again, we started with the assumption that the point is in the plane, which is this line up here. And when that's not true, we get something that makes no sense. So now we've verified that it's not in the plane. So now we can start using our distance formula. So first thing we need to do is we need to find all of our information. We have our point P, which is 10, 3, negative 8. We have our normal, which we got from our equation. We just take our A, B, C values from our equation of a plane. And it becomes 4, 2, negative 1. Sorry, I put these look like round brackets. I'm going to make them square brackets. And then we need a point Q to finish this off. Now, point Q is just some point inside the plane. Any point will work for us. So all you're going to do is pick any x and y you want and solve for z. We're going to keep it easy, and we're going to solve for x equals 1, y equals 1. And if you do it correctly, you should get z equals 10. And again, that looks a little messy, so I'm going to tidy that up a bit. So for this specific point, again, any point on the plane will work, but in this case, we got 1, 1, 10, so we're going to use that. Now we just need to find vector PQ in our formula. So that's we're going to take point Q and subtract point P. So that becomes 1 minus 10, which is negative 9, 1 minus 3, which is negative 2, and then 10 minus negative 8, which is positive 18. So now we have our normal, we have our vector PQ, which connects a point to a point on the plane. Now we can plug them in and solve. So remember, our formula was, D equals the absolute value of the normal dot product with PQ over the magnitude of n. So that becomes 421 dot negative 9, negative 2, positive 18 over 421 with our big horizontal lines. And remember, this can apply as absolute value or as magnitude. So we're going to just see what we get from our top and our bottom. On the top, that's dot product, so that turns into some scalar values. That's going to become an absolute value. So we just do our dot product, and it becomes negative 36 minus 4 minus 18, and then we're going to take the absolute value of that, which is 22. On the bottom, because it's a vector, we use the magnitude formula, which gives us 4 squared plus 2 squared plus 1 squared, all square rooted, which becomes root 21. And then we just rationalize it and simplify it if we can. We can't reduce root 21 anymore. So our final result here is 22 root 21 over 21. And that's the result in exact values. So if it's an application problem, you'll want to solve it as a decimal place if it's more suitable, in which case you can write it as 4.80 units. But if we're just looking for the exact value, just 22 root 21 over 21 is going to be just fine. So hopefully that sheds a little light on distance between point in a plane and intersection between lines and planes. Again, if you have any questions, come and check in with me and we will sort it all out. Thank you, and I'll see you in the next lesson, which is intersection of planes.